Hello and welcome to lecture number 7, which is on direct kinematics or forward kinematics. In the last class, we looked at transformations, that is, how do you go from the end effector frame to the base frame by using the transformation matrices. Now, today we'll look at the next topic, which is direct kinematics, that is, given the joint variables theta1, theta2, theta3, how do you find the position orientation of the end effector with reference to the base coordinate frame. Okay, so today's topic is forward kinematics, and in forward kinematics we are going to find the position and orientation of the end effector, and the input to that is my theta1, theta2, theta3, which are the joint variables in case of revolute joint systems, or d1, d2 in case of translating joint system. So we will start off by looking at the inverse kinematics problem like this. So let's draw a very simple manipulator, which is 3 degrees of freedom. So it is, my first joint is here, okay, second joint is here, and third joint is here. Now we are going to assign our frames as per DH convention, and we have done this quite a few times before, so I'll do it very quickly. Z0, Z1 is here, Z2 is here, Z3 is here, and X0, X1, X2, and X3. What are the joint variables? It is theta1, theta2, and theta3. Now we can make a DH parameter table very quickly, A, alpha, D, and theta, and here I can populate the table 1, 2, 3. So that's my 3 joints. So it is 0, 0, 0, theta 1. The link length is L1 here, and this is L2, and this is L1, 0, 0, theta 2, and this is L2, 0, 0, theta 3. Okay. Now what we are going to do is, I'm going to find the transformation matrices, which is going to relate the third frame with the 0 frame, and we have seen the 3 matrices come out of the form T0 to 1, which is given by cos 1 minus sin 1, sin 1 cos 1, 0, 0, 1, 0, 0, and this is 0, 0, 0, 0, 0, 0, 1. This is the first one. The second one is would be T1 to 2, which is given by, so I take one row of this, put it in the generalized matrix, and this is how I get it. So it is cos 2 minus sin 2. It is sin 2 cos 2, 0, 0, 1, 0, 0, 0, 0, 0. Here it is L1, 0, 0, 1. And the third one is 2 to 3, which is given by cos 3 minus sin 3, sin 3 cos 3, 0, 0, 1, 0, 0. And here it is L2, 0, 0, 0, 0, 0, 1. Okay. Now I want to find the relation between the third frame and the first frame. So what do? We multiply all the matrices together. So I multiply this into this into this. So I'm going to get T0 to 3. This also I did in the last class. So please have a look at that. What we are going to get is cos 1, 2, 3 minus sin 1, 2, 3, sin 1, 2, 3, cos 1, 2, 3. 0, 0, 1, here it is 0, 0, 1, 0, 0, 0, and here I'll get L1 cos 1 plus L2 cos 1, 2, and here I'll get L1 sin 1 plus L2 sin 1, 2. This will be 0, that will be 1. Okay, please refer to the previous classes, so that when I derived it very slowly, and we showed how do we get this matrix. Now this is the final matrix T0 to 3, which gives the relation of the third frame with reference to the 0 frame. Now this matrix has 4 parts. We have the rotation part, and we have the translation part, right? So let me draw it again a little bit clearly so that we understand better. So this is my manipulator, and this is my theta 1, theta 2, and theta 3. Okay, and my matrix came out as T0 to 3, which is equal to cos 1, 2, 3 minus sin 1, 2, 3, sin 1, 2, 3, cos 1, 2, 3, 0, 0, 1, 0, 0, 0, 0, 0. This is L1 cos 1 plus L2 cos 1, 2. This is L1 sin 1 plus L2 sin 1, 2, 0, 1. Okay. Now we have 4 parts of this matrix, and these 4 parts are, these are the 4 parts of the matrix. Okay. So this is the rotation part, this is the translation, Okay, this is perspective and this is scale. This is something we know. Now, what does the rotation part tell us? Rotation part tells us that what is the total rotation in terms of the orientation of the end effector. What do we mean by the position and orientation of the end effector? I mean this point. So what is the xy of this point? What is the position of this point? So the position of this point is x, y. This is 2D, so there is only x and y. What is that? And what is the orientation of the end effector with respect to the base frame? Okay. So what this tells me is the rotation or the orientation of the end effector. Okay. And this tells me the position of the end effector. Okay. So this column here is the position x, y, and z, and this is the rotation of the end effector with reference to the base frame. So in the direct kinematics problem, so we also call it forward kinematics. Okay, forward kinematics problem. What is the input? The input is my thetas. In this particular case, it is thetas or link variables. Let's call them link variables. It can be thetas or it can be d's in case of translating joint. So this is my forward kinematics, also called direct kinematics, means the same thing. What is the output? It is the position and orientation. Position plus orientation of end effector. So what is the position of the end effector? The position of the end effector is given here. So this is my position of the end effector. Okay, x, y, and z. What is the orientation of the end effector? The orientation of the end effector is this matrix. So that is the orientation of the end effector. So what does this tell me? That you can see here it is cos theta 1 plus theta 2 plus theta 3. So the orientation of the end effector is the sum of theta 1 plus theta 2 plus theta 3. This is my x-axis, that's my y-axis. Okay. Then the orientation of this is equal to theta 1 plus theta. This is my horizontal. So it is theta 1. This is my theta 1. That's my theta 2. So theta 1, theta 2, and theta 3. So this total is theta 1 plus theta 2 plus theta 3. So that is the orientation of the end effector. What is the position? It is the position of this point. So we have projected down here. What is it equal to? It is equal to this much, which is equal to L1 cos 1, and this much, which is equal to L2 cos 1, 2. Okay. So this is the position of the end effector in the x direction, and in the y direction it is this much plus this much. So this is equal to L1 sin 1, and this is L2 sin 1, 2. Okay. So what is L1, L2? L1, L2 are the link lengths. So this is the meaning of position and orientation of the end effector. How did we get it? Please note, first we assigned DH parameters. Okay, or we assign the frames. Okay, by following the DH method, from which we derive the DH parameter table. Now we took the DH parameter table each row at a time and got this matrices which relates one frame to the other frame, right? Then what we got is this is the first one, then the second one, and the third one. Then what did we do? We multiplied all these three and we got our 0 to third frame, which is given by this matrix. Now this final matrix gives us the position and the orientation of the end effector with reference to the base frame. For the orientation is the rotation part, and position is the translation part of the homogeneous matrix. Okay. So what is forward kinematics or direct kinematics? The input to this is the thetas, and the output is going to be the position orientation of the end effector. So in this matrix, suppose I give the values of thetas. Let's take an example of this matrix again. So just for example, let me look at so my matrix was cos 1, 2, 3 minus sin 1, 2, 3. It was 0, 0, 1. It is sin 1, 2, 3 cos 1, 2, 3 0, 0, 1. It is L1 cos 1 plus L2. It is L2 cos 1, 2. Okay, here it is L1 sin 1 plus L2 sin 1, 2. It is 0. It is 0, 0, 0, and 1. So it means that if the input given theta 1, theta 2, and theta 3 given values means numerical values. Okay, we can find we can find what is the position plus orientation of end effector. Okay. So what I need to do is I simply need to take, for example, I give the example theta 1 is equal to 30 degrees, theta 2 is equal to 40 degrees, and theta 3 is equal to 60 degrees. So I take this, put it in this matrix, and I'm going to get the numerical values of what is the position and what is the orientation. L1, L2 are known. Okay. Now what is the position? Position is going to become this one, and orientation is going to become this. So in forward kinematics, my input is thetas in this particular case, and what is the output? It is xy of the end effector. Okay, and the orientation, which is the matrix. So the procedure is the same for all manipulators. First assign frames, then write DH parameter table, then find the transformation matrices, then multiply them all out and look at the final matrix. This is the final matrix T0 to 3 in this case, and this gives the orientation part. This is the orientation part, and that is the position part of the end effector. So in the forward direction, it is not very difficult to do. Let's look at another example of forward kinematics. Let's look at the Scara manipulator, where we are looking at, we had done this example also in the last class. So we have the Scara manipulator, which is 4 degree of freedom. Okay, so we are going to assign our axis as per DH notations. So these are my axes. The third one and the fourth one is here. So this is my Z0, Z1. This is Z2. This is Z3, and this is my Z4. And for simplicity, I'm taking the origins here. So my X1, X0, and X1 is coming here. X2 is coming there. X3 is there, and X4 is here. This is revolute. This is the prismatic joint. So there is a motion of T. Okay, so there is theta 1, theta 2, and theta 4 here. Okay, so now the first thing we do is to make our DH table. Please refer to the last few classes. I have explained it slowly. I'm doing it very fast here. Now these are my joints 1, 2, 3, and 4. What is the DH table? For the first is 0, 0, 0, theta 1, then it is L1, 0, 0, theta 2, then it is L2, 0, 0, theta 3, and sorry, there is no theta 3. So D3 is there. This is my D3, the translating joint. This is 0, and this is 0, 180, L2, and theta 4. This is my DH table. Now, taking each row at a time, we can put in the generalized matrix and get our generalized matrix as T0 to 1 is equal to cos 1 minus sin 1, sin 1 cos 1, 0, 0, 1, 0, 0. This is equal to 0, 0, 0, and 0, 0, 0, 1. This is my first matrix. The second matrix, 1 to 2. 1 to 2 is given by cos 2 minus sin 2, 0, 0, 1, sin 2 cos 2, 0, 0, 1. It is L1, 0, 0, 0, 0, 0, 1. Okay. What about the third one? T2 to 3 is equal to, the third matrix is going to become, you look at here, there is no theta there. Okay. The variable is D3. So as there is no theta, there cannot be a rotation. So this will be a identity matrix 0, 0, 0, 1, and L2, 0, D3, and 1. That's my the third matrix, and the fourth one is going to become T3 to 4, which is given by cos 4 minus sin 4 minus sin 4 minus cos 4, 0, 0, minus 1, 0, 0. This is 0, 0, 0, and it is 0, 0 minus L2. Now, you should look at this very, very carefully and try to understand the correlation between the matrix and the manipulator. Okay, that is something very, very important in robotics, that we have to understand the correlation between the matrices, that is the mathematics and the manipulator structure. So if you look at this manipulator from the top view, okay, from here, if I see, what you'll see is that there are two links actually. This is like a two-link manipulator. What I'm trying to say is that we did this problem, okay, of our basically three-link manipulator, but the first two links, this link and then this link, is the same as the first two links of this Scara robot. Okay, then the third one is a prismatic joint, and the fourth one is a revolute joint again. So what I'm saying is, if you see from the top view, if I draw this manipulator from the top, okay, so this is my side view. Okay, so this is the side view. Now if I see the top view, what will you see? You'll see one manipulator structure like this. Okay, this is another one like that. Okay, this is what you'll see, and this is the base of the robot. This is the top view. Okay, so this is my top view of the manipulator. Okay, now if you see the top view, it is basically behaving like a two-arm system, two-link system only. So what do I mean by two-link system? It is behaving like this kind of a system. Okay, so there is one theta 1 here, there is one theta 2 here. This is the same structure there. There is a theta 1 here, and there is a theta 2 there. So when it is moving, it will move like this only. Now I hope you can visualize theta 1, theta 2. What am I trying to say? So in this kind of structure, if you see, it is exactly same as this one. Okay, so whatever is coming from here in terms of the matrices, let's look at the matrices again. Here, if you look at the first matrix and you look at the second one, you look at the DH parameter table here, they are exactly the same. So you should be able to correlate this and understand what is the relationship between the matrix and the manipulator when it is moving in space. So this is a Scara robot, which from the top view appears like a 2 degree of freedom arm. So the DH parameter table for the first two joints is same. The third joint, there is a prismatic joint which is moving perpendicular to this joint. Okay, so let's go back to this again. Yeah, so the matrices that we are seeing, the matrices that I wrote here, the first one and the second one is for 2 degree of freedom system, which is exactly same. Okay, now the third one is here, which is a prismatic joint. So this is there is no rotation there, a prismatic joint which is D3 is the variable. So that is where it is coming. Okay, now the fourth one is a rotation matrix again. There is a rotation in terms of theta 4, but if you note, the z's are in different directions. So Z3 is upwards, whereas Z4 is downward. So there is a 180 degree shift, and that 180 degree cos of 180 is minus, so that is why this minus is coming here. So if you note that this minus has come here. Now why did this minus come? Because the z changed direction. Okay, so you should be able to correlate this and understand the matrix in terms of the structure of the manipulator. Let's see further. So this is coming from the top. If you look from the top, basically you can see this is behaving like a two-link system only. Now when we multiply them all out, I take all the matrices, multiply them out. You can do that. Okay, it's just matrix multiplication. I will just write the final solution. So the final solution T0 to 4 will come out as, I'm just writing the final solution, cos 1 2 cos 4 plus sine 1 2 sine 4. Or well, when I was explaining in terms of two-link manipulator, let me write all of it. So T0 to 4 is equal to T0 to 1, T1 to 2, T2 to 3, and 2, 3 to 4. Now this much is a two-link system. Okay, so the matrix for these two will be, so T01 to T1 to 2 will be exactly the same as that of a two-link system. So cos 1 2 minus sine 1 2, sine 1 2 cos 1 2, 0 0 1 0 0 0 0 0. This is L1 cos 1 plus L2 cos, this is L1 cos, right, L1 cos 1, so L1 sine 1, this is my 0, and this is 1. Okay, so this is exactly same as a two-link manipulator system, where theta 1 theta 2 is there. So if you look at this one, okay, so this is my theta 1, this is my theta 2, this is L1, this is L2. So when I multiply the first two matrices, what I'll be getting is this one. Let's look at the first two matrices again. Yeah, so this is one matrix and this is the second one. So when I multiply them out, okay, what I'll be getting is this one. Next, I multiply this with T2 to 3. Okay, so multiply 2 to 3. What I'll be getting is cos 1 2 minus sine 1 2, sine 1 2 cos 1 2, 0 0 1 0 0, and what we get is L1 cos 1 plus L2 cos 1 2, L1 sine 1 plus L2 sine 1 2, that is 0, that is 0 0 0 1. Okay, now sorry, there is a D3 here. Okay, yeah, D3 is the variable. Now look at this matrix. Okay, look at the rotation part and look at the position vector here. Okay, you see that it is very similar to this one. Okay, it is very similar to this matrix. So what we got here is cos 1, 2, 3. In the previous case, I'm getting cos theta 1 plus theta 2 because there's no theta 3. The theta 3, this is a prismatic joint, so the theta 3 comes in terms of the D4, D3. Okay, so in terms of the matrix multiplications, you should be able to correlate. Okay, depending on the structure of the manipulator, the matrices are going to appear in a particular form. So in the two-link system, we got cos theta 1 plus theta 2 plus theta 3. Now there is no theta 3 here, so it is cos theta 1 plus theta 2. Okay, and the x coordinate is L1 cos 1 plus L2 cos 1, 2. It is same as that one. Okay, so this is the x, y, and here we have a D3. Okay, now I multiply this with the fourth one, cos 4 minus sin 4, it is 0, 0. So it is minus sin 4 minus cos 4, 0, 0. So this is 0, 0, minus 1, minus L2, 0, 0, 0, and 1. Okay, so when I multiply this out, what do we get in terms of the final matrix is T 0 to 4. 0 to 4 is equal to cos 1, 2, cos 4 plus sin 1, 2, sin 4 minus cos 1, 2, sin 4 plus sin 1, 2, cos 4, 0. Here it is L1 cos 1 plus L2 cos 1, 2, and here it is sin 1, 2, cos 4 minus cos 1, 2, sin 4, minus sin 1, 2, sin 4 minus cos 1, 2, cos 4. Here it is 0, so it is L1 sin 1 plus L2 sin 1, 2. Here it is 0, 0, minus 1, minus L2 plus D3, and here it is 0, 0, 0. Okay, so let's this is the final matrix T0 to 4. We need to understand what this means in terms of the manipulator structure. Actually, that's more important than just simply writing matrices. Now when we look at this, what you see is this is my L1, this is my L2, this is my theta 1, this is my theta 2. Okay, so this point here is actually L1 C1 plus L2 C1 2, and if you see it from the top, it is like a two-link system. Okay, this is a two-link system only. Okay, so it is like this, the two-link system. So that's my theta 1, this is my theta 2, this is L1, that's L2. So the prismatic joint is perpendicular to the plane here. Okay, so if theta 1 and theta 2 changes, there will be no change on the z coordinate. Okay, because theta 1 and theta 2 are moving on the xy plane now. So this is my, what I mean is this is z, that is x. So and y is that side. So when theta 1, theta 2 changes, it's this point changes on the xy plane only. There is no change on z. So that is the reason why this is L1 cos 1 and L2 cos 1, 2. Similarly, the y coordinate is in terms of sine. So L1 sine 1 plus L2 sine 1, 2. Now what about z? This is the z coordinate. Now the z coordinate of this origin, right? This is my z4. This is my x4. So when this moves up and down, what will happen is D3 is the variable. So this will vary. Plus there is a fixed distance L2 there. Okay, the physical length. So the total is minus L2, minus because it's on the bottom direction, plus D3. That is the total length of Z. Okay. So if theta 1, theta 2 changes, it has no effect on Z because it moves on the xy plane. But if D3 changes, what happens? This end effector goes up or it comes down. Okay, so now you understand physically in terms of this, what this matrix means in terms of the manipulator structure. And this is my rotation part. Okay, so which is equal to, sorry, this full one here is my rotation part. This one shows that the z-axis has reversed. Okay, so the first z0, z1 is, z0 is upward and z4 is downward, and that is shown from here. Okay, so now we can correlate each of these matrices and try to understand the relation between each of the matrices as we proceed. Now you can do this for, we have done for two examples, a two-link manipulator, and I did it for the Scara manipulator. You can do it for other manipulators. So here we have four variables, theta 1, theta 2, D3, and theta 4. Okay, So if I give this as input to my forward kinematics program, what we'll be getting is output, and the output is going to become that matrix, which is the position and the orientation of the end effector. This is the meaning of the forward kinematics problem, or direct kinematics, right? So the input is theta 1, theta 2, d3 and theta 4 numerical values. I know the link lengths L1, L2, so it will tell you what is the position orientation of that point. Position plus orientation in terms of this matrix. Now let's move on to a little bit more difficult problem that we were looking at in the last class. So in the last class we looked at the Puma robot, right? So this was our Puma manipulator, and we assigned frames to this in a particular way. So how did we assign frames to the Puma manipulator? We saw which are the axis of rotation, and then we assigned our z-axis, then our x-axis, and then we wrote our DH parameter table. That's what we did. So very quickly I'll go through this. For details, please refer to the previous lecture where I went very slowly and I explained. Now here we are assigning our axis depending on the rotation. So my first rotation is here, so theta 1. Second rotation is about z2, theta 2. This is my third, theta 3. And theta 4 is about here, so that's theta 4. So this part is shown there. So that's my theta 4. Then theta 5, my z5 is that side, and z6 is back this side again. Okay. So when I'm putting my x-axis, they have been z1, z2 are intersecting. So x0, x1 are perpendicular to the plane. x3 is here. x4 is upward. So x4, x5, and x6 are perpendicular, are in the same axis, So if I look at the DH parameter table now, let me write the DH table. Our DH parameter table is A, alpha, D, and theta. Okay, this is 6 degrees of freedom, so there are 6 thetas, and this is 1, 2, 3, 4, 5, and 6. Something to note here is this axis 6, z-axis 6 and z-axis 4 are along the same direction. That is essentially to enable us to write our DH parameter properly. In reality, it is orthogonal. So this is something that I had mentioned in the last class also, that in reality the axes are orthogonal, which means that your z4 is this side, z5 is that side, and z6 is this side. This is called the roll, then this is called the roll, pitch, and the yaw motions. Okay, roll, pitch, yaw. But if I rotate it about this axis, what will happen is, if I pitch, what will happen is, if I rotate about this axis, what will happen? This axis z is going to come down. Okay, and if it comes down, then it can get aligned with the so z6 can come here. Okay, so it is relative axis. That is the reason why it is done like this in the for writing the DH parameter table. So please note this point. Now what we are doing is we are writing our DH parameter table, and our table comes out like this: A, alpha, D, and theta. So the first one, you see the axes are the same, so 0, 0, 0, theta 1. So in most manipulators, theta 1, your first axis and the 0 axis will be the same in terms of frames. The Z2 is rotating by 90 degrees about the x. So sorry, Z1 is rotating by 90 degrees about the x-axis, and it's becoming Z2. So this is minus 90. Okay, this one is 0, 0. This is theta 1. Sorry, theta 2. Okay, the third one is where is the third axis? The third axis is here. Okay, that is my Z3. Now Z2 and Z3 are parallel, so there is no distance here. Okay. They are a parallel axis, but you can see that there is an axis shift here, shift of the origin. What I mean is, if you look at the origin of frame 1, it is here. Frame 1, frame 2 origin is here, whereas for frame 3 origin is there. So it is like it has moved this side, then it has moved like this. So there are two distances. Okay, this is your one distance here, okay, which is your A2, and there is another distance which is your D3 here. Okay, so A2 and D3 are given here, A2 is given here, and D3 is given there. So by putting that in, what we get is 0, A2, D3, and theta 3. And for the fourth one, we get minus 90, A3, D4, theta 4. Okay. And then we get 90, 0 0 theta 5, theta 5. The last one is minus 90 0 0 theta 6. So please note the motion of the z-axis, especially at the wrist, which is here. Okay, so theta x, so your z3 is here. It rotates by 90 degrees, okay, clockwise about the x-axis, becomes z5. Okay, so there is a minus 90 here. Then z5 rotates anti-clockwise. Z4 rotates anti-clockwise about the x-axis and becomes z5. So there is a plus 90. Then z5 again rotates clockwise and becomes z6. So there is a minus 90. So at the wrist there is a clockwise, anti-clockwise, and then clockwise rotation again. But the last three axes are intersecting at that point. Now this is a 6 degree of freedom system. So what we do is we have to write the transformation matrices from one frame to the other frame, and then we can multiply all of them to get our final transformation matrix between the 6th frame and the 0 frame. Okay, so what we do next is we have the generalized matrix, and in the generalized matrix we take each row at one time. So every time I take one row and then I put them in the generalized matrix, and what happens is I get the transformation matrices for each frame to frame transformation. So let us do that, and when we do that, what we get is t0 to 1 is equal to, so the first one is always the same. You'll note cos 1 minus sin 1, cos 1, 0 0 1 0 0, this is 0 0 0, this is 0 0 0 1. It's interesting that in most revolute joint robots, the first axis and the first transformation matrix is the same. The second one, there is a rotation of 90 degrees, so what we get is 1 to 2. Okay, and this is cos 2 minus sin 2, this is 0 1 0 0, there is minus sin 2 minus cos 2, 0, so there is 0 0 0 1 0 0 0. The third one is t2 to 3, which is equal to cos 3 minus sin 3 cos 3, 0 0 1 0 0 1 here, and it is a2 0 d3 1. So I hope you understand how do we get these matrices. We are essentially taking one row at a time, putting it in the generalized matrix which we wrote in the last class, and then we proceed. Okay, now this is my 2 to 3, 3 to 4 is given here. So 3 to 4 is cos 4 minus sin 4, 0 0 1. This is minus sin 4 minus cos 4, 0 0. This is a3 d4, 0 1. Okay, this is the third to fourth, fourth to fifth, 4 to 5 is equal to cos 5 minus sin 5, then this is 0 0, sin 5 cos 5, 0 minus 1 0, this is equal to 0 0 0 1 0 0 0, and the final matrix comes out to be equal to 5 to 6, which is equal to cos 6 minus sin 6, 0 1 0 0, this is minus sin 6 cos 6 minus sin 6, minus sin 6 minus cos 6, 0, this is 0 0 0 and 0 0 0 1. Okay, so how did we get it? We simply took each of these fellows and put it in the generalized matrix. So what was the generalized matrix? If I write it again, okay, so the generalized matrix which I wrote in the last class, I will just write it here again. T I minus 1 to I. The generalized matrix was cos theta minus sin theta, 0 ai. Okay. Then it was cos theta, sin theta cos alpha. Okay, sin theta cos alpha, cos theta cos alpha. This is minus sin alpha, and here it is minus sin alpha d. The third one is sin theta sin alpha, cos theta sin alpha, and this is cos alpha, and the last one is cos alpha into d. Okay, so this is 0 0 0 1. This is the generalized matrix. So what we do is take one row of this, put it in the generalized matrix, and get our transformation matrices. Now you realize something is that If you have to do this by hand, it's very cumbersome and you're going to make a mistake somewhere. Okay, so what is done is we write a computer program either in MATLAB or in C language, and then what we do is we try and then we just simply multiply the matrices and get our final matrix. Now in this Puma robot, what we need to note is there is a particular way of multiplying. Okay, let's start off by multiplying the matrices in the case of the Puma robot and see what we end up with. So we are going to multiply in a particular way, okay, and it will become clear why we are going to multiply in that particular way. Okay, so as I go along, I will explain why we are doing it like that. So what we say is T0 to 6 is equal to T0 to 1, T1 to 2, T2 to 3, T3 to 4, 4 to 5, and T5 to 6. So there are 6 of them. 1, 2, 3, 4, 5, 6 matrices are there. Okay. So how we multiply is we first multiply these 3 matrices. Okay, that's what we do. Then we multiply these 2 matrices and then multiply these 2, and finally lastly we multiply that 1 matrix. So I will go in this direction. So I'll multiply these 3 first. Okay, then I will multiply this one into this, then I will multiply with T1. Okay, so this is the direction. The other way we could multiply is we can multiply 1 to 3 and 1 to 6. So we are going to multiply in a particular sequence, and then we are going to observe some interesting properties. So what we'll do is we are going to observe some interesting properties by multiplying this to this. Okay. Now what it basically means, if you look in terms of variables, then T0 to 6, okay, T0 to 1, T1 to 2, T2 to 3, and T3 to 4, T4 to 5, and T5 to 6. What are the variables here? This theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6. These are the variables, right? The other linked lengths and all are all constants. So if I multiply this many, so it will contain theta 2, theta 3, theta 4, theta 5, and theta 6. Okay, it will not have theta 1. Why? Because we are not multiplying with this one. Now, why are we doing it like this? If you go back a little bit and observe that, let's look at this example, the two-link manipulator case. So if you're looking at the two-link manipulator case, what we observe is that if you look at the last matrix that comes out of it, where's the two-link? This is Scara. So if you look at this one, you find that the x coordinate and the y coordinate has combinations of theta 1 and theta 2, and this one is equal, that's the x coordinate, which is L1 theta 1 cos theta 1 plus L2 cos theta 1 plus theta 2. This is what it means, right? Now you're seeing that this theta 1 and theta 2 are coming in various combinations. It is coming in cos theta 1 plus theta 2. In this case, it is sin theta 1 plus theta 2. So actually solving for this equation when we come to inverse kinematics is very difficult. Okay, and because of which this is what makes inverse kinematics extremely difficult. So to avoid that, we are trying to see in terms of inverse kinematics how is it possible to solve for this. Okay, and what has been observed is essentially if you multiply it like this, your variables, if you multiply like this, you'll have a combination of theta 1, theta 3, theta 4, theta 5, theta 6, but your theta 1 will not be there. Why? Because I'm multiplying from T1 to 2 up to T5 to 6. Okay, so if you multiply it like this, we get this matrix. Let me call this T5 to 6. Okay, T5 to 6 is R11, R11, R12, R13, R14. This is, let's call this my Px, this is my Py, and this is my Pz. Okay, so these are R21, R22, R23, R31, R32, and R33. This is always 0, 0, 0. This is always 1. Okay, these are all very long expressions. So I'm just simply saying that if you multiply it out, you'll get this many terms. This is going to be my rotation, the orientation, and this is going to be my position. Okay, so when you multiply it out, what we do get is this terms. So R11 in the previous case, this is my R11. So what is R11 equal to? Okay, R11 is equal to cos theta 2 plus theta 3 into cos theta 4 into cos theta 5 into cos theta 6 minus sine theta 4 into sine theta 6 minus sine theta 2 plus sine theta 3 into sine theta 5 into sine theta 6. So you can see that this is a quite cumbersome expression. Okay. Now similarly, R21, 23, then 31, 12, 22, and 32. Okay, this is what we are getting. Okay, for each of these terms. So each of these terms, I'm writing it there. This. Okay, so this is 3 by 3 matrix for the rotation part. So the 3 by 3 matrix comes like this. So this is the 3 by 3 rotation part or the orientation part. Okay. Now you can observe that there is no theta 1. So there is no theta 1 anywhere here because we did not consider t0 to 1. Okay. Now if you look at this, if you look at the position part, this is my position part, you see something very interesting here. Now what you see very interesting is that this is pz. What you see very interesting here is that for a particular py, this term, it does not have this fellow. Let me write it in red color, as you we need to remember this. This does not have any thetas. Okay, so please note this. Okay, so it is very strange that this particular term, which is the py, it does not have any thetas associated with it, no joint variables. It only has d3, which is a constant. Okay. Whereas all other terms have cos, sine, and all kinds of other terms. And only if you multiply it like this, then you get it like this. Okay, then it turns out in this form. Now, what is py in the previous case? So py is this term. Okay, so this is equal to d3, and all the other terms are functions of sine and cos. Now, if you were to multiply t01, let me go back here. So if you were to multiply t01 into this, okay, so this into t01. Sorry, this is t1. Sorry, please note this is t1 to 6. Now, if you were to multiply t0 to 1 into this t1 to 6, then what you'll get is this matrix. Okay, now this matrix is equal to t0 to 6 is equal to R11, R12, R13. This is Px, Py, Pz with respect to the end effector. So let me call it E. Okay, so this is R21. This is R21. This is R22 and R23. This is R31, R32, and R33. Okay, this is with respect to end effector. So let me call it, or this is with respect to the base. So let me call it B. Reference to 0 frame probably. Okay, so this is with reference to base frame, so 0 frame. So let me call it this. Now, if we look at this, okay, this is equal to t0 to 1 into t5 to 6, which we got in the last time. So 5 to 6. Okay. Now, if you look at each of these terms, R11, okay, which is here. So let's call them R110, okay, indicating this is with reference to the base frame. Okay. So in each of these cases, you see that all the terms have sine and cos, and there is no term which does not have sine and cos. Okay. So a note very, very carefully here that if you were to multiply t0 to 1, t1 to 2, okay, in that way, like this up to t5 to 6, and come up with t0 to 6, then what we'll get is this set of numbers, this set of expressions, which show that all the terms have sine and cos, and there is no term which does not have sine and cos. Now, why does this happen? Now, this actually happens because of some very interesting properties. When we come to inverse kinematics, we'll look at those. Okay. So, for the Puma manipulator, how did we get the final transformation matrix? Exactly the same way. What we did is we assigned axis, then we wrote our DH parameter table, and from the DH parameter table, we found the transformation matrices from one frame to the other frame, put it into by using the generalized matrix. Then I multiplied all of them out in a particular way. Now, what was that particular way? It was essentially multiplying T1 to 2 up to T5 to 6, and we left out T0 to 1. That is essentially done because if you do it like that, then theta 1 is not included in the final expression, and we end up with one term, okay, which is my py, which does not have any sine and a cos. So something to note. Now let's move on now to the next part. So in the forward kinematics problem, we saw that when we say the input was my joint variables. Okay, so input I'm giving the thetas or the d's. Okay, rotation. This is a revolute joint, or this is a prismatic joint, depending on whatever the manipulator is. And in my forward kinematics, output is my position and orientation plus orientation of end effector. Okay. Now, if I take the position and orientation of the end effector, or let me look at it like this, which one is more important when we have a manipulator like this? Okay. I have theta 1, theta 2, and theta 3 here, and I want to go from one position to another position. I want to go from here to here now. Okay, something like this, just for example. So it was here, it has gone there now. Now what has happened? Theta 1 has changed to theta 1 dash. This has become theta 2 dash, and that has become theta 3 dash. Okay. Now how does the robot manipulator actually work? So there is a motor there, and there is a position sensor encoder at the back, and there's a gear in front. Okay. So what the controller does is, at every position and orientation of the end effector, it needs to know what is theta 1, theta 2, theta 3. Okay. That means we can say that the position and end effector, position plus orientation of the end effector is a function of theta 1 up to theta n. Okay. Now, at every position of the end effector, the controller needs to know what is the theta 1, theta 2, theta 3. Okay. Now, and how will it know? And it can find out by doing what is called the inverse kinematics now. So in inverse kinematics, what is done is we give the input as the position and orientation from here, like this. And this is my inverse kinematics now. Okay. So the input to the inverse kinematics is the position orientation of the end effector, and the output of the inverse kinematics is my joint angles. Okay. So we see what is forward kinematics, what is inverse kinematics. Now from control point of view, inverse kinematics is more important. Why? Because at every position, the controller needs to know what is the position orientation of the joints. Okay. So in terms of control, how does the robot manipulator actually work? Okay. So suppose we are at position 1, and this is at position 1 or location 1. We want to go to location 2. So at location 1, what it will do, it will find the corresponding joint angles theta 1, theta 2, theta 3 by doing inverse kinematics. Then I want to go from here to here. So in location 2, it will again do inverse kinematics and find out what is theta 1 dash, theta 2 dash, theta 3 dash. Okay. Then what it will do theta 1 dash minus theta 1 and generate an error called del E1. Similarly, it will get an error there, del E2, and from here it will get del E3. So it will do this minus this. So it will do 2 minus 1 and get an error. Then what the controller will do is it understands that there is an error, that I was here, I want to go to theta 1 dash, but I'm here. So I need to move by how much? I need to move by theta 1 dash minus theta 1. I need to move that much, which is this much. So if I make that equal to 0, okay, it is as good as saying that it should move the joint in this direction until that error becomes 0. And that is how the manipulator moves. So the controller, what it does, at every position and orientation of the end effector, or every desired position orientation of the end effector, it has to find what is the corresponding angles. And then it knows I want to go here, and this is my present position. So it is desired minus present position and orientation. It generates an error. And then it drives it in that direction. Drives means what? It gives a voltage to the motor. The motor rotates, the link rotates in that particular direction, and the error goes towards 0. The moment it reaches 0 means it has reached the position. That's how the controller works. Now, in order for the controller to work, the inverse problem is more important. as far as kinematics is considered. Okay, because at every location it has to find what is the corresponding joint angles and then try and drive it to the desired position. So that is an inverse kinematics problem. So from control point of view, inverse kinematics is more important than forward kinematics. Now we have seen that the kinematic equations contain sine and cos terms. Okay, in all kinds, multiplication, addition. So trying to solve this kinematic equation becomes a little bit difficult. Now what we mean by solving? What we mean by solving is, I have a two-link manipulator here. Okay. So this is my two-link manipulator. This is theta 1, theta 2 and theta 3. And what is my position and orientation, final position and orientation? Let us say it is cos phi, okay, minus sin phi, cos phi. This is 0, 0, 1, that is 0, 0. This is 0, 0, 0. What is this one equal to? This is equal to x, y and z. Okay, in this particular case this is 0, that is 1. So this one is my x-axis, that's my y-axis, right? So this point has an xy, which is xy, this is which is xy given here. This is 0. This is the rotation, okay, or the orientation of the end effector. This is the position of the end effector. This is equal to what we can find the relation between the third frame and the 0th frame. We just found it some time back. This is given by cos 1, 2, 3 minus sin 1, 2, 3, sin 1, 2, 3, cos 1, 2, 3. This is 0, 0, 1. This is 0, 0. That is 0, 0, 0. This is L1 cos 1 plus L2 cos 1, 2. This is L1 sin 1 plus L2 sin 1, 2. This is 0. That is 1. Okay. So the inverse kinematics problem, we said, is given the position and orientation of the end effector, you have to find the joint angles. Okay. Now, what is the meaning of given the position orientation of the end effector? It means that I'm going to give you this matrix, numerical values. Okay. For example, cos of this phi. What is phi equal to? Phi is equal to theta 1 plus theta 2 plus theta 3. Numerical values. So I'm going to give you this. Okay. Numerical values of that. And we have to find what is the corresponding angles which will get me to that point. Okay. So now what we see here is that this is a 4 by 4 matrix. This is also a 4 by 4 matrix. Okay. So if I equate term by term, how many equations will I get? So I'm going to equate this term with this term. Okay, this term with this term. Okay, this term with this term, and then try and solve. So the inverse kinematics problem, I'm given the position and orientation of the end effector. This is my position, that's my orientation in terms of numbers, and this is the T0 to 3 matrix, the third frame to the base frame matrix. Now I'm going to relate or equate term to term and see if I can solve. What am I trying to solve for? I'm trying to find what is the corresponding theta 1, theta 2 and theta 3 for any position orientation given. Now if I equate term by term, how many equations I'll get? I'll get 16 equations. Okay, it's 4 by 4. But all these equations are of no use, because you can see that this is 0, 0, 0, that is 1. This is 0, 0, 0, that is 1. So 0 equal to 0 doesn't mean anything, right? Again, here also if you equate, you'll not get any meaningful equation. There is no variable there, right? Similarly, here if you see, again, it is 0, 0, 0, it is 1. So writing equation 0 equal to 0, 1 equal to 1 does not mean anything. You cannot solve for theta 1, theta 2, theta 3. And this term, okay, and this term, say cos phi is equal to, if I equate with there, cos theta 1 plus theta 2 plus theta 3. Okay, this is an equation, but you cannot solve. Okay, this term equations are difficult to solve. In this particular case, you will not be able to solve. Okay, so this brings us to the problem of inverse kinematics. That inverse kinematics is difficult compared to forward kinematics, and because there are sine and cos terms, and sine and cos terms have, you know that sine and cos have for every theta, for every value it will have 2 thetas, right? So for example, sine 90 and sine 270 is the same number, it's 1, right? So it will mean that you will have multiple solutions. So first of all, it is difficult to solve, then there are multiple solutions, and that is what makes inverse kinematics difficult. What do we mean by multiple solutions? If we have a tool-link arm like this, okay, this is one solution, one xy. What is the other solution? This is the other solution. Okay, this is the xy is the same, but theta 1 and theta 2 are different. So this is theta 1 dashed, and that is theta 2. Okay, so that's a minus theta 2. Okay, so this shows that for the same xy you can get two pairs of theta 1. So we have theta 1, theta 2, and you have theta 1 dashed and theta 2 dashed. So these are two solutions. Now if you have more degrees of freedom, you can have more solutions. Okay, so for example 6 degrees of freedom manipulator can have more number of solutions. So this is what makes inverse kinematics difficult as compared to forward kinematics. And there is a standard way of trying to solve this inverse kinematics problem, which we'll be seeing in the next class. So in the next class, what we'll be doing is, after our forward kinematics, which I have discussed today, I will be going towards inverse kinematics in the next class. Now, so what I would suggest is that please go through the DH parameter assignment. The frame assignment is extremely interesting, and it's not only interesting, but it's important. Okay, that if you cannot get your DH parameters right, then you cannot do inverse kinematics anyway. And for large manipulators, it's not very easy, but once you systematically apply you assign the frames, then it's easy to get your DH parameter table and then get your transformation matrices, and from there you can get your the relationship between the last frame and the zeroth frame. Now, using that position and orientation matrix, what you can do is we can get forward kinematics if you're given the joint variables, and what is more important is the inverse kinematics. That means, given a position and orientation of the end effector in space, how would you get the corresponding joint angles? Because the controller needs those joint angles to move the robot to a desired position. So we will stop here today, and in the next class we are going to start with inverse kinematics. Please go through DH parameter assignments and take some examples. There are a lot of examples in textbooks. I have also done some examples in this lecture. So go through all of them, and then we'll be ready for the inverse kinematics in the next class. So we'll stop here today. So thank you.